Next speaker is Fiedler Berthold. And um, please show your presentation.
Yes, if you let me share contents, yes. So let me share my screen.
So, very interesting title, Real Chaos and Complex.
Yes.
And complex type.
Thank you very much. It's a little provocative. Can you hear me all right?
Yes, very good.
Okay. So let me first thank the organizers for the opportunity to speak at this conference where a lot of expertise, perhaps the world top expertise on homoclinic and heteroclinic orbits is combined. And I want to talk about something which kept bothering me for about 25 years concerning the complex time extension of homoclinic orbits in analytic vector fields. And this is related to exponential smallness questions, exponentially small splittings of separatrices, which is supposed to be governed by poles of the real homoclinic orbit in complex time. So the distance of the pole from the real axis, the imaginary part of time it takes to reach a singularity, is what rules this exponential smallness. And one of the questions I want to address, well, is there any such pole or such singularity, or could it be that they are entire homoclinic orbits? Now, a lot of people have helped me and have have contributed to the topic also. And here's a very incomplete list of who is who in this field. I will mention some of these names in the talk. So first of all, I want to address connecting orbits, and in real coordinates, x dot is f of x, real vector fields, we talk about a connecting orbit which, say, runs from an equilibrium at t equals minus infinity. Of course, autonomous we are here, in infinite time to another equilibrium, v plus somewhere. So this is the homoclinic, I call it gamma for Russian reference, contour, which is our primary object here. Now, let me briefly mention that time periodic rapid forcing of a period, so in t over epsilon, period equals 1 here. So in time we have an epsilon periodic forcing is the same as time discretization. With a forcing like this, if we pass to a stroboscope map, so we have the non-autonomous evolution with parameter epsilon, and we are looking at time t for that. If we look at time epsilon and repeat that, we get an iteration, which I abbreviated by this. So in a way, now you know what sex is, okay? So it's the time epsilon stroboscope map of this epsilon periodically forced system. But on the other hand, we can also discretize the true flow with an error, of course, a local discretization error for time step epsilon. In numerics, they call it h. And so the error is also of order epsilon to the p plus 1, just with as with a forcing of amplitude epsilon p, epsilon to power p before. And therefore, we can talk about something called backwards error analysis, which says, well, let's look at the non-autonomous evolution, which depends on the non-autonomous forcing. But can we choose a non-autonomous forcing such that this exact solution of the slightly wrong vector field is the discretization which we had? And yes, that is possible, and that's called backward error analysis. And so a rapid periodic forcing is the same as discretization. So therefore, we can just look at what happens to a homoclinic orbit of an autonomous vector field under discretization. And of course, in continuous time in the plane, for example, for a pendulum, we expect a closed contour, whereas under discrete time, we expect transversality. And if you try this out with the pendulum, a second order pendulum, explicit Euler, you add a little bit of friction, you see, because the Euler step transports you outside a homoclinic loop, then you see a picture like that. And the point is you have to enlarge at a step size of 0.2, where along the homoclinic orbit, this is macroscopically visible hops of the discrete scheme. So not a very good discretization, of course, most stupid possible discretization, nothing against Euler, great man, of course, connecting Berlin and St. Petersburg. You have to enlarge by a factor 10 to the 21 an order 1 homoclinic orbit near the origin in order to see the picture that we expect for a discrete system. So the system, yes, we have transversality, but the transversality is extremely small in the step size. And of course, there are theorems about that. And let me just mention an upper exponential estimate, which Jürgen Scheuerle and I presented about 25 years ago. This was published. We looked at the following. We said, let's look at x dot is f of lambda x autonomous, the unperturbed, and then add a discretization or a rapid periodic forcing. So here in T over epsilon, we again have period 1 in T over epsilon. So period epsilon in T, epsilon small. And let's look what happens as epsilon tends to 0. Now for epsilon equals 0, we assume a transverse homoclinic orbit to a hyperbolic equilibrium. And this is in Rn now. So here we are in Rn, or rather because we assume that F is entire and G is entire in X, it cannot be in T because you have to match things. So at best you can assume smoothness here. So, but in Rn versus Cn for the complex time extension, we have that this homoclinic orbit by real analyticity is complex analytic in a small complex time strip. Okay, a small strip, imaginary part of T less equal eta. And of course, we will take eta as large as possible for the complex time extension of this homoclinic orbit. Now for epsilon equals 0, I said there is a transversality. That means that the stable and unstable manifold cross each other at non-zero speed. Melnikov function with respect to lambda has a simple 0 at lambda equals 0. And then the result was with some tricks and a little bit of functional analysis and this and that, that the splitting interval, which is a measure for, so L epsilon tells you
Bernard,
how discrete, yes?
Bernard, sorry. The number P enters somehow to the estimate or not?
Yes, in C.
In C, okay.
Yeah, so we don't have, well, you could have an epsilon to the P in front here, but of course the -1 over epsilon kills any such finite order effect. The epsilon P is here. So there is like a systematic deviation of the place lambda where you see splitting, which is of order epsilon to the P. Okay, but the width of this interval, so how large is separatrix splitting? That is what we measure by the length of the splitting interval in terms of lambda. And that is a constant times exponential times minus another constant which is related to the complex time extension divided by epsilon, 1 over epsilon. So this is infinite order small, even though our discretization, for example, is first order. Okay. So this tongue here is even sharper than the tongue of dear Arnold. Now, many people have worked on that, and I should mention pioneering work, of course, by Anatoly Neistat in 1984 on adiabatic elimination. So he said that by averaging methods, when you have an epsilon periodic forcing, you can get an exponential estimate, exponentially close to the time epsilon map of an autonomous vector field for some positive constant. Eta. Now we related this eta to the complex time extension of the homoclinic orbit in our special case. I should also mention early work on the pendulum equation by Phil Holmes, Jerry Martin, Jürgen Scheule with lower estimates. And the grandmaster, of course, was Wassily Gelfreich, based on work by Lasutkin, who gave very detailed, I mean, much more detailed results than the crude upper estimate that I just provided, with like meromorphic expansions by very careful analysis near the pole of the homoclinic orbit. Carlos Simo has talked many times in our conference series here on Hamiltonian case and about discretizations. Carsten Mattis has extended this exponentially small splitting upper estimates to parabolic partial differential equations, and jointly with Arne Scheel to Hamiltonian like wave type equations. I want to mention Heire and Lubich, the numerical guys, on backwards error analysis, and finally Claudia Wolf and others on symplectic partial differential equations and numerical discretization of those. So the PDE results are based on very, very regular solutions, spatially extremely regular solutions of Jevry classes. So that's exponentially decaying Fourier modes or Galerkin modes. But how about entire homoclinic orbits? Couldn't it happen that we have a homoclinic orbit for an entire vector field, so globally convergent power series for f of x? Think of a polynomial, vector polynomial. And couldn't it happen that we encounter a homoclinic orbit which is without singularity in the whole complex plane? The problem is, and that's why I'm talking here, I'm seeking your advice on this matter. I do not have a single such example. Now, you guys know infinitely more about homoclinic orbits and things like that. And I will try to present a result which ensures the occurrence of singularities. But I do not have any example of an entire homoclinic orbit of an autonomous system, no matter what. It should be entire F, of course. So what could happen is local singularities. We have x dot is x of n. We can, of course, separate variables here and see how we get a Riemann surface and how we get blow up in finite time, also for x dot equals e to the x. And I would like to mention as an aside that Masuda, very early, and then later a student of mine, Hannes Stuke, have exploited and studied blow up for partial differential equations, trying to blow up, which is called complete by dear colleagues in PDE, trying to circumvent the blow up moment, the real blow up time in imaginary, by an imaginary detour to continue the solution behind blow up. Very interesting work, which I cannot talk about today. So how about entire homoclinic orbits? So assume you have an entire homoclinic orbit. Now, the following corollary to the work with Jürgen Scheule may be void. if there does not exist such an entire homoclinic orbit, okay? But let me still show you what would happen so you know what to look for. If we had an entire homoclinic orbit, then we can apply the result with Jürgen Scheuerle on any arbitrarily wide imaginary strip. Any strip of arbitrarily large imaginary width around the real time axis. And this means that we would get super exponential estimates for any eta. In fact, if you think about it for a little moment, and this is not a deep consequence of the previous result, it's almost trivial, you can estimate L of epsilon in the form exponential minus a function of 1 over epsilon. Before this was eta times 1 over epsilon. Now this is a convex function, eta of r, which with slope increasing to infinity as r goes to infinity or epsilon goes to 0. So this is exponential estimate with arbitrarily large slopes. In particular, there could of course not be a lower splitting estimate of the form constant over epsilon, like we had in all cases which were studied so far. So how about a complex singularity? Perhaps we can prove in some cases that a homoclinic orbit does possess a complex singularity. And in the planar case, we have such results. But let me now go to n dimensions. And I have to talk a little bit about complex time here now. So complex time flow, I start with an entire globally holomorphic, globally convergent power series, right-hand side. And if you like, you can assume that f is real for real arguments, but you don't have to assume that. So we get a local flow now in complex time, and I split complex time into real part sigma, that's the ordinary time, and the imaginary time direction. And these flows commute, okay? So phi t composed with phi s is phi t plus s, as always. And as a corollary, the real time and the imaginary time flow, they commute with each other. If f happens to be real for real arguments, then the flow is in addition reversible in the imaginary time direction, which tells us that there will be a lot of oscillation in the imaginary time direction. Reversible flows are a little bit like Hamiltonian in that respect. So do we have a complex singularity? Let us assume that we have a connecting orbit between two equilibria. And by connecting orbit, of course, we mean gamma is not identically constant. Well, for this equation, very cheaply, just by Liouville theorem, we know that each component of that orbit, and we are working in any finite dimension here, any component must, of course, be unbounded for complex time, unless that component is identically constant so that the source and target equilibrium coincide in those components. So any such component must be unbound. Fine. That's Liouville theorem. But how unbounded? Unbounded doesn't mean it has a singularity at finite imaginary distance from the real axis. It could be unbounded as the imaginary part of t tends to infinity. Huh? So this does not preclude singularities. Now let me prepare for a theorem which does prove that certain homoclinic orbits or heteroclinic orbits must have singularities. And with this, I look at the linearization of the vector field at the source and target equilibrium. So we remember, of course, we have V minus and we have V plus, and we have our heteroclinic orbit. And here I have the linearization A minus and over there A plus. And so I'm looking at the stable spectrum at the target A plus, And I'm looking at the unstable spectrum, the stable spectrum of minus A minus. I'm looking at the unstable spectrum of where I come from. So let mu j be the eigenvalues and let those be real, only real eigenvalues. So that's why I'm hoping that in Chilnikov type homoclinic cases, maybe we find entire homoclinic orbits, but I don't know. So I have to assume real eigenvalues and non-resonance. Now, what is the advantage of that? If I'm at non-resonance, then going in the imaginary time direction, I find quasi-periodic orbits for large negative real parts, so near V minus, and for large positive real parts, that is near V plus. I find quasi-periodicity in imaginary time. And the second theorem says, under the same assumptions, that indeed the homoclinic or heteroclinic orbit must be singular. It can never be entire. So blow-up occurs in finite imaginary time somewhere here. So here is my real time, real t is sigma. Here is my imaginary part of t, which is tau. And somewhere, maybe here, I have a singularity. And therefore, the eta that we get for exponential estimates cannot reach beyond that singular point. And we get an exponential upper estimate. Now, we cannot prove super exponential estimates, but then hopefully smart people like Vasily Yevreich or others will prove also lower exponential estimates. Now, complex linearization helps here. So as a tool, let me consider x dot is f of x locally near x equals 0 equilibrium and assume A is hyperbolic, non-resonant. And we are in the Poincaré situation that is 0 is not in the convex hull of the linearization. Then Poincaré proved classical result that you can locally analytically linearize X by a near identity transformation to completely linear flow. Very nice. We are going to use that. Now, to prove the first theorem, which said that solutions near our equilibria are quasi-periodic in imaginary time, we only look in, say, in the unstable manifold. We have non-resonance there. Since all eigenvalues are in the unstable manifold are unstable, we can forget this Poincaré domain assumption and apply Poincaré linearization. We get that gamma of t locally takes the form, takes this form. And now because the mu j I tau remain 1 in the imaginary time direction, this whole thing remains small. The local linearization applies, and we do get quasi-periodicity by an explicit representation of a torus flow. Now, to get the complex singularity, to prove theorem 2, which asserted that gamma cannot be entire, we look at the Fourier series for large positive or negative real part of time. We get this Fourier series by Bohr-Besicovitch, very classical theory, where the Fourier coefficients, these omegas are, of course, non-negative integer combinations of the eigenvalues here. And the imaginary time comes from the I tau here. No? The time makes this imaginary. The Fourier coefficients are the ordinary Fourier coefficients, except you take an ergodic average here, okay, for t, capital T to infinity, of the actual solution. Next, suppose indirectly that our homoclinic or heteroclinic contour gamma is entire. Then I can do Cauchy integration. So here is sigma real time, here is tau, And I can take a fixed but large interval. So I take absolute value of sigma very large. So a sigma minus here and a sigma plus. And then I choose an imaginary time such that gamma, here is gamma of sigma, the real part. And this solution is very close to gamma of sigma, arbitrarily close if I go large enough with tk, the imaginary time part. And so integrating over on the left is the same as integrating over the right, because the horizontal parts almost cancel and are divided by tk. Now, if we insert in this expression for the Fourier coefficients, if we insert omega equals 0, then the first thing we note is that our entire orbit must be homoclinic. Another reason to talk to Shilnikov people. Combining, question? Okay, combining the first and the second step, I get that gamma of t has such a representation, but maybe not in between, because you see quasi-periodicity in the imaginary time direction in particular means that you have boundedness in the imaginary time direction. Now, this boundedness may get lost somewhere in between that a priori boundedness, but I can still expand. The series will not converge in between, but for large positive and negative sigma, it will converge, and the C's are the same. These exponentially decorated Fourier terms have to be the same. However, at large negative real time, we are in an unstable manifold, so we cannot have negative frequencies here. We cannot have minus omega t. And for large positive sigma, we cannot have positive Fourier coefficients, which are non-zero. Therefore, our gamma of t is identically constant and is not a connecting orbit. And we have proved by contradiction that any heteroclinic or homoclinic orbit with these real non-resonant eigenvalues at source and target must have a singularity. And of course, if you are in planar situations of saddles, then the unstable eigenvalue is a single real eigenvalue, and the stable is a single real eigenvalue. And therefore, this always takes care of the planar case without any further assumptions. Towards the end of my talk, let me briefly address something I stumbled across, namely anti-holomorphic gradient flows. I just want to hear your opinion. I have been helped by Alejandro Koshar, my dear friend Carlos Rocha, a longtime co-author, and combinatorial guy Tibor Sabo at Berlin. What do I mean by an anti-holomorphic gradient flow? I mean this equation. So I'm taking like a complex gradient flow. Z dot is minus W prime of Z. Gradient, the prime is derivative with respect to Z, and we have several variables here, but I take a complex conjugate. If I do this just for the fun of it, then Cauchy-Riemann tells me that X dot is a gradient vector field with respect to the real part of the W. But it is also Hamiltonian with respect to the imaginary part. So here we have a class of vector fields, which we can consider in R2n, which are at the same time gradient and Hamiltonian. Usually these are completely separate communities, right? I mean, gradient people have gradient flows, and Hamiltonian people have gradient flows after the Lagrange point of view, maybe, but not directly in one vector field combined. So I thought this is a very strange example. And let me show you what happens at a simple zero of W prime with these anti-meromorphic flows, if you like. You get for the imaginary part, the level set of here's a critical point, W prime equals 0 and equilibrium. You have unstable and stable manifold. And the colors are a heat map for the real part. So brown means you are on a high mountain, and blue means you're in the deep sea. It's a geographic heat map, not a frequency heat map. And so the stable manifold is this thing of that equilibrium. If you have a double zero or a higher zero, you get several branches here. At a pole, say at a double pole, you can regularize the flow to consist of 1/2 a source and 1/2 a sink on the other side. And if a triple pole, you get 2 sources and 2 sinks. You get 1 less sources than the degree of the pole. Now for anti-polynomial flows, let me do an example where W prime, so it's this polynomial with 0, Z1 to Zn. And I can regularize at infinity to find a pole of order n plus 2 at infinity, which means that infinity has n plus 1 sources and n plus 1 sinks. Here's an example with n equals 4, 1, 2, 3, 4, 5 sources at infinity, 4 plus 1, same number of sinks. And here with the gammas, with the contours gammas, I have indicated the stable manifolds of the hyperbolic equilibria in the finite. All equilibria, because of the Hamiltonian gradient structure, must be hyperbolic. Now, if you draw this schematically, then you obtain these sources at infinity, which I put at the vertices of a regular polygon. And I draw the stable manifolds as straight lines. I could use a curve shortening for that. And I see that these flows by orbit equivalence correspond 1-to-1 to such circle diagrams. And these diagrams are known in combinatorics as non-crossing trees. So for any tree, you can draw in a circle by putting the vertices on the boundary and the edges like arches, chords in the trees, sections of the tree. Now this opens the door to 2 types of theorems. This is all scalar, right? Anti-polynomial flows of degree n plus 1 correspond 1-to-1 to these non-crossing trees. And therefore you can count them. You can count them, and fortunately a smart guy did this for me, Mark Noy, in 1998, gave explicit formulas for the number of such trees. This is not tree counting. This is counting the trees up to, embedded into the circle, up to dihedral symmetry. So the same topological tree may have several representations. And here I drew all the 7 examples with 5 vertices at infinity corresponding to polynomials of degree 4. So there are these 7 cases. Duality corresponds to time reversal. And I have drawn 2 times 5, 10 diagrams here, but the right 3 are self-dual. If you pass from the black to the red, which is reverse time, you get the same thing here. Let me skip the remaining results to leave a little bit of time for discussion and pass to a summary. So there is a way back from the, let me show this maybe. There's a way back from the meromorphic functions from the story which I just told about anti-holomorphic flows, because I can just multiply by W and get a fraction to see that this flow is equivalent up to an Euler multiplier to -1/W. And now the poles of this W are, of course, the zeros of Z, and give you flows Z dot is -A inverse Z, so you can have periodic orbits and the like. Okay, so there's a possibility to get periodic orbits. Well, to summarize, I started with real connecting orbits. and which lead to exponentially small splittings. I showed that for real non-resonant eigenvalues, we do encounter a complex time singularity at finite imaginary distance from the real axis due to imaginary time blowup. And please remember, I'm not aware of any example of a homoclinic orbit which is entire yet, or a heteroclinic orbit. Thank you very much for your attention, and I'm looking forward to your advice.
Миша, ты что замолчал?
I have a question.
Yes, please.
Hi, Bernard.
I said, but I was
My,
sound.
Misha, I ask, okay?
Thank you very much. Questions?
In principle, because sigma and tau are independent variables, you can consider two boundary cases. For example, pure imagery time and pure real time.
Yes.
Pure real time we know, pure imagery time we assume that we know because it's the same in some sense. What difference between these boundary cases in behavior on the monoclinic orbits?
Well, you see, let me answer for the planar case. Okay. And I assume you're not talking about the anti-holomorphic flows, but for homoclinic contours. Yes. So if you have a homoclinic orbit in imaginary time, then you see that inherited from the left, you have a Hopf bifurcation situation. You have like a Hamiltonian center theorem, and if you have a real like f of x bar is f of x bar, so if you have a real start from a real vector field, then you get periodic orbits in imaginary time rather than the hyperbolic structure.
Yeah.
Now the periodic orbits tell you that well, once you have imaginary periodicity at the left of your imaginary plane, maybe over here for you, then it is periodic in imaginary time everywhere. And then the homoclinic orbit is bounded. And then the homoclinic orbit is constant by Liouville theorem. And this is what I'm circumventing with the quasi-periodicity. Now for quasi-periodicity, it is not true that if you start with quasi-periodic, you are globally quasi-periodic, because you always miss, you know, I mean, the complex structure is not, or identity theorem for power series is not strong enough to assert the same quasi-periodicity everywhere. It does not propagate, but you have it only on the left and only on the right. So you have to do some tricks. And if eigenvalues are not real, then in imaginary time, you may leave neighborhood, because imaginary time just rotates the spectrum by 90 degrees. You know, then the stable eigenvalues may contribute to unstable and so on. You have real parts of the eigenvalues and you are in a lot of trouble, even if they are just a little bit complex. You know, I mean, if you have a double real eigenvalue at resonance, at real resonance, you can split that and it will make, in imaginary time, your eigenvalues will walk away. They will leave the neighborhood of linearization.
It may maybe depend on edge value of fixed point, for example. If
yes,
fixed point,
but how? I mean, we have such smart people here who have studied resonances.
Okay.
You see, I have no clue. I have no clue.
Saddle focus transform to saddle transform to saddle focus.
Please try.
Yeah.
Okay. Yeah, you can try saddle focus. You can try saddle node, and perhaps you find something without singularity. I have absolutely no clue.
Okay. Thank you.
It's not just like dear Dimatoraev, who always claims he has no clue what he talks about. I have proved I have no clue. Okay.
Okay.
He knows what he talks about. I don't. Okay.
I understand. Okay.
Very good.
Why I'm mentioned here? I
So
have
one-
nothing to do with this complex time. Sorry,
Yes.
I have nothing to do with complex time. You mentioned my name. Sorry, no,
Yes.
no, that's it. That's it. Just
No, I was just you. I'm always
It's okay,
impressed
yes.
when you start your talk by saying you don't know what you're talking about. Okay.
okay.
So this time, I hope I have proved that I have no clue of what I'm talking about.
Sorry.
Complex time is a complete mystery for me. Okay.
So we need to go to the next talks. So thank you once again, and let us.
Well, thank you.